How many times do you run, walk, jump in just one day? And what would you do if it hurt every time you did it? 1 in 20 adults over the age of 25 will require some form of knee replacement surgery a year. The common reason for knee replacement surgery is easing chronic pain. That means the quality of life of these individuals is solely dependent on the quality of the design and manufacturing of these implants.
History. The knee implant was first introduced and implanted by the doctor Themistocles Gluck in 1860. This design consisted only of a hinge joint made of iron. In the 1960s, surgeon John Charnley conducted a hip replacement surgery using an implant made from polyethylene and metal. This hip implant would go on to inspire the current design of the knee implant. A decade later, Frank Gunson improved the hinge joint aspect of the knee implant up until the 70s, when modern-day cruciate ligament implants were designed. Now, instead of singular surgeons and inventors, major companies Stryker, Smith & Nephew, Zimmer Biomet, and Depot Synthes work to improve the knee implant.
When designing the knee implant, engineers must take into account many aspects of the knee's anatomy in order to produce an optimal design for a knee implant, such as complexities of geometry, soft tissues, forces, muscle movements, insulation, and so forth.
Mechanics. A knee functions as a hinge for the human body, which determines the movement of a person. The knee not only determines the movement of the body, but also must support the entire weight of a person and can experience 3 to 7 times a person's body weight just from walking alone. To put it simply, the knee is 2 leg bones held together by muscles, ligaments, and tendons. In the knee, 2 long bones, the femur and tibia, roll on each other to create a movement which is separated by the meniscus in order to prevent bone damage. The ligaments and tendons work to secure the bones and hold them in place. Safety. Arguably, the most important aspect when designing a knee implant is the safety of the patient during and after placement. Both the material used and the structure of the knee implant must take into account the biology and anatomy of the knee. This means knee implants must be made out of biocompatible materials, and manufacturing must be performed while still maintaining a safe and sterile environment.
The following knee implant is known as a posterior stabilized knee implant, which means the posterior cruciate ligament inside of the knee is replaced by the implant. It takes on the function of the PCL, which prevents the thigh bone from sliding too far on the shin bone when bending the knee. This implant is composed of 3 parts: the femoral element, tibial insert, and tibial element. For installation, when the implant is installed, the damaged ends of the shin bone and thigh bone are removed. Then, a cemented prothesis is attached to each of the bones with cement. As the bone heals, the new bone grows into the surface of the implant, becoming a portion of the knee.
A second type of knee implant exists, which is known as the cruciate retaining implant. As the name suggests, the PCL is preserved while the ACL is removed. The design differs because it no longer has the center post and cam design. Instead, it relies on a natural anatomy of the patient's knee to provide stability and function. The cruciate retaining implant allows for more natural knee movement and mimics the biomechanics of the original knee more closely. It is often preferred for patients with a healthy posterior cruciate ligament and suitable for those who have only one damaged ligament. This type of implant may offer advantages in terms of preserving proprioception and preventing the potential complications associated with removing both cruciate ligaments. Proprioception refers to the body's ability to sense its position and movements in space, which is essential for balanced coordination and joint stability. By maintaining the PCL, the cruciate retaining implant helps preserve the sensory input that allows the patient to better control their knee movements. Partial knee implants are another alternative for quicker recovery and targeted treatment of specific areas of the knee affected by arthritis or injury. Unlike total knee replacement, which involves replacing the entire knee joint, partial knee implants only replace the damaged part of the knee. This approach preserves healthy bone, ligaments, and cartilage, leading to faster recovery times, reduced pain, and improved function. Partial knee implants are suitable for patients with localized arthritis or damage primarily affecting one compartment of the knee, such as the medial, lateral, or patellofemoral compartments. By retaining healthy tissue and bone, partial knee implants offer a more conservative treatment option while providing effective relief from pain and restoring mobility. Additionally, because the surgery is less invasive, patients typically experience less blood loss, shorter hospital stays, and quicker rehabilitation compared to a total knee replacement procedure. After the design of the knee implant is completed, manufacturing must be done. Knee implants are commonly made using additive manufacturing, which refers to processes that produce an object one layer at a time, based off of a computer-aided design model. The most difficult part to manufacture is the femoral component of the knee implant, due to the curvature of the bone and the variations present from person to person. So additive manufacturing provides several benefits such as producing complicated shapes, dimensional accuracy, and high customizability. The plastic component of the implant are often manufactured through extrusion, injection, and compression molding. As previously stated, manufacturing methods must also maintain safety. One common risk comes from the oil emulsions produced during the machining process, which can cause infections in implants, putting the wearer's life at risk. To improve safety, implants are coated to improve resistance to radiation, friction, temperature, and bacteria. This is performed using a spraying process known as vapor deposition. Before insertion, knee implants are tested using joint implant simulations, then they are finally shipped to hospitals.
In order to manufacture the knee implant to be long-lasting, the materials used in the implant must be taken into account. The main criteria for the materials are that it needs to be strong enough to withstand the forces applied to the knee between the ground and person, flexible enough to not break from the stress, smooth enough to not get caught in the other parts, and biocompatible so it is not rejected by the body. The metal portions of the implant, such as the femoral component and tibial component, are typically made of titanium or cobalt chromium-based metal alloys. Meanwhile, the plastic spacer is typically made of medical-grade polyethylene, which is fatigue-resistant, safe, and non-toxic. The choice of material and manufacturing methods allow knee implants to be customizable to the needs, anatomy, age, weight, and activity levels of the patient, which is necessary to improve the quality of life of the patient.
Improvement, trends, and innovations. Despite all the knowledge, money, and effort that has gone into the creation of the modern implant, problems still exist within the current design. Knee implants often have to be replaced after failure of the polyethylene components due to oxidation. Knee implants must be replaced after 20 years, which is both expensive and physically traumatic for patients, so improvements are continuously made on the design and manufacturing of them. Over the past decade, 3D printing has been widely recognized, but recently, 4D printing has come into the limelight. 4D printing is a similar additive manufacturing process as 3D printing. However, the material interacts with external stimuli. This could be beneficial for the future of implants because implants could then respond to the forces, mechanics, and biology of the patient for better quality fit and a longer lasting life.
Furthermore, advancements in computer-assisted design, CAD, and simulation technologies allow for virtual modeling and testing of implant designs before production, ensuring that final products meets the patient's individual needs and provides optimal performance. This personalized approach to knee implantation not only enhances the efficacy of treatment, but also minimizes the risk of complications and reduces the need for revision surgeries. As such, the ongoing development of customizable knee implants represents a significant step forward in the field of orthopedic surgery, offering patients the opportunity for a more active and pain-free lifestyle.
So next time you're walking up the stairs or going for a run, take a moment to think about the decades of research and development that went to make sure you can still do all of the activities you love years down the line.